A video by special request on how to convert a geometric sequence into an exponential function. All right, let's lock in. So we're trying to learn how to convert a geometric sequence to an exponential function. And then we're going to study those exponential functions a little bit, but it helps to kind of understand the connection between the two. First thing we're going to do is review a little bit. In the left, we have a geometric sequence where this is referred to as our nth term. G sub 1 is our first term. R is denoted as our common ratio. And then, of course, we have our exponent of n minus 1. If we look over at the function notation, which is where we're going to be moving, our function of n in this case is equal to, well, the a value is actually the y-intercept. So a little bit different than it is in the geometric sequence. That a value is actually the y-intercept. This r value is still the common ratio. And then, of course, we have our exponent of n. So the issue is here, how do we convert from one to the other? Well, let's take an example. So we have 2 times 3 to the n minus 1. That's our geometric sequence. Before we get going, let's take a look at what that looks like on Desmos. This is what our geometric sequence looks like on Desmos. And we're going to take note of the fact that it is a series of dots. It starts at 2, and I've filled out the table you can see there. Multiplied by 3 is 6, multiplied by 3 is 18, and so on. It is a discrete function in that it only exists at exactly those points. Now, what we're going to try to do is find a function that fits those discrete points. So back over our example equation, 2 times 3 to the n minus 1. First thing we're going to do is we're going to keep the 2, and then we're going to apply that product rule to break up the 3 into 3 to the n times 3 to the minus 1. And that's our product rule of exponents. We're allowed to take that 3 and just break up that n and negative 1 because we have the same base. We can split those things up. Now, the second exponent rule we need to apply, we're going to bring down the 2. We're going to bring down the 3 to the n. But we know that 3 to the minus 1 is simply equal to 1 over 3. Well, now we're getting there. We have a 3 and a 1/3. Those are constants. And we can multiply those things together. Well, 2 times 1/3 is simply 2 over 3. And we bring down our 3 to the n, and we're there. We can now put it in function notation, and we have converted that geometric sequence into a function where this is our y-intercept and 3 is our common ratio. And that's really all there is to it. Now, back over in Desmos, we still have our geometric sequence plotted, that series of dots. But if we plot our new function, we can see it fits those dots perfectly. Okay, we've got another example problem here. So let's just walk through this a little bit more quickly this time. First thing we're going to do is split up those exponents in 2 to the n and 2 to the minus 1. Next thing we're going to do is rewrite that 2 to the minus 1 as 1 over 2. Next thing we're going to do is multiply this 4 and this 1/2. 4 times 1/2 is 2. We bring down our 2 to the n, put it in function notation, and that is literally all there is to it. Okay, I hope that helps. I'll see you in class.